All right, let's finish out these notes here. I think we left off on this example where we were examining the similarities and the comparisons between the graph of a function and its derivative here. So we said this was a picture of what 1/3 x cubed minus x looks like, where we had a relative max at x equals -1 and a relative min at x equals 1. Then on our graph of the derivative, we can see that here, since the slope of my original function is 0, the actual value of the derivative is equal to 0, and same here, since the slope of my original function is 0, the actual value is 0 here. Then we can look at the comparisons to the second derivative, right? So we said that our original function had a point of inflection at 0, right? So right here, we can see that my function changes from concave down to concave up. Well, we said that's where the second derivative equaled 0. But it turns out that here, that is a place where the slope of the first derivative equals 0. So if I scroll down a little bit here, we said that we had a point of inflection at 0, and the second derivative was negative to the left of 0 and positive to the right of 0. Now, in terms of the original function, right, that told me that f, the original function, was concave down here. So concave down, and over here, my original function was concave up. But if I think about what's going on with the derivative, right, what's happening with f prime here? Well, on this interval, my derivative, my f prime, is decreasing. Okay, the slope is negative. Well, let me write it like this. Let me say the slope is decreasing, or the function is decreasing. So we'll just say that f prime is decreasing on that interval. F double prime, the second derivative, is the first derivative of f prime. So if f prime is decreasing, f double prime is negative. Hopefully that makes a little bit of sense. Likewise, if my second derivative is positive, that means that my first derivative is increasing. All right, and we'll take a look at this comparison more in just a second. Right? So on the back then, sketching out points of inflection. Here we just kind of want to examine graphically, where that occurs, what that means. Well, we want to try to find the point where we change from concave up to concave down, right? And it might not be an exact science, but it looks like that's going to occur, somewhere right in here. Right? We change from my function facing up to my function facing down. Now, if we think about the tangent line, right? Today in class we said that the tangent line, wherever my function is concave up, is below the function, and wherever my function is concave down, the tangent line is above the function. So at a point of inflection, the tangent line actually crosses, that wasn't a real good tangent line, it actually crosses the function. Right? Same idea here. It appears as though my point of inflection occurs, maybe somewhere in there, where I change from concave down to concave up. So same idea. If I draw my tangent line in there, it looks like my tangent line here will be pretty close to horizontal. It will cross the function there. Right? Really similar idea over here. My function changes, I don't know, maybe somewhere right in there. And if I sketch out my tangent line, at that spot, it's going to cross the function. Right? So let's take a look at another example here. Right? We want to determine any points of inflection and discuss the concavity of this function. So let's take our derivative. So the derivative would be 4x cubed minus 12x squared. Right? Now, if I want to, the question does not say to do this, right? It just says find points of inflection and talk about concavity. But if we wanted to find increasing, decreasing, and relative mins and maxes, we would set this equal to 0 and solve. But let's just jump into second derivative. So second derivative will be 12x squared minus 24x. So to find possible points of inflection, set this equal to 0. I can factor out a 12x, and I'm just left with x minus 2. So now I can set each of these factors equal to 0. This one would give me x equals 0, and this one would give me x equals 2. So those are my two possible points of inflection, and I'm going to put those two values on my sign chart for the second derivative. Remember to label your sign charts. This way you know which function to plug your test points into. So we need to choose a value less than 0. We'd say -1. So if I plug -1 in, well, this will be a negative, 12 times -1, and then this would be a negative. So I've got a negative times a negative. That's going to be a positive. If I plug in a value in between 0 and 2, say 1, this will be positive. 1 minus 2 is negative, so a positive times a negative is a negative. And then if I plug in a value greater than 2, say 3, this will be positive, this will be positive, so positive times a positive is a positive. So what this tells me is that my function, my original function, right? So I can say since the second derivative is positive on these intervals, my original function, f, is concave up on the intervals -infinity to 0 and 2 to infinity, and then concave down on the interval 0 to 2. And then since I do change concavity at both of these points, we can say we have points of inflection, which we'll abbreviate POI, at x equals 0 and x equals 2. So that answers every part of the question, right? Determine any points of inflection, so at these two values, and concave up on these intervals and concave down on this interval. Now we could, depending on how the question's worded, right? I guess technically, since this says points, we should plug these two values back into the original function to determine the entire point. So let's go ahead and do that. So if I plug 0 into my original function, I'll have 0 minus 0. So one of my points of inflection is 0, 0. And if I plug 2 in, 2 to the 4th is 16 minus 4 times 8 is 32, so 16 minus 32 is -16. So those are my 2 points of inflection, 0, 0, and 2, -16. All right. So the next two, let's kind of take a look at this idea on a calculator a little bit. So I think this is supposed to be pi, right? Not p, so 2 pi. So we want to find how many times the graph changes concavity. Well, to do that, we need to know what the second derivative is, even if we're going to use a calculator. So let's find the second derivative. So y prime would be 2x minus 0. The derivative of 3 would be 0. Now here we actually have to use chain rule, right? So the derivative of sine is cosine. So plus cosine, don't change the inside, then times the derivative of the inside, right? Now my second derivative, derivative of 2x is 2, derivative of cosine is negative sine of 2x minus 1 times 2, then times the derivative of the inside. So I'll actually have another factor of 2 here. So I can write this a little bit nicer and say 2 minus, if I bring the 4 out front, so 2 times 2 is 4 times the sine of 2x minus 1. All right, so now my goal is to determine how many times my original graph changes concavity. So what I want to know is how many points of inflection do I have on the interval 0 to 2 pi. Okay, well, to do that, we set our second derivative equal to 0, but now it says I can use a calculator. So what I want to do is take this and plug this into y equals on my calculator. Right, 2 minus 4 sine of 2x minus 1. Now it says I just want the interval 0 to 2 pi, so I'm going to go into my window and change this to be 0 to 2 pi. Now let's see what this looks like. Okay, now remember, this is the second derivative of my original function. Points of inflection occur where the second derivative changes sign. That happens here, 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 and here, right? So what we can say is my function, my original function, changes concavity 4 times on the interval 0 to 2 pi because the second derivative changes sign 4 times on the interval 0 to 2 pi, right? So our answer is 4 times, and we could write out that explanation, right? The second derivative changes sign 4 times, therefore the original function changes concavity 4 times on the interval 0 to 2 pi, all right? The next one is another calculator active one, right? Again, we just want to figure out the values where this function changes concavity. So again, to do that, we need the second derivative. To take the derivative here, I'm going to have to use product rule. So why don't you guys take a second and try to find the first derivative and then the second derivative. All right, so my first derivative, if I'm using product rule, y prime, will be the derivative of the first. So derivative of e to the x is just e to the x times the second plus the first times the derivative of the second. Right? Now, I can clean this up a little bit, factor an e to the x out of both of these terms, and just make this e to the x times the quantity x squared plus 2x. This will actually make finding the second derivative a little bit easier, because if I left it like this, I would have to do product rule twice, right? I have to do product rule with this term, and then product rule with this term. If I write it like this, I just have to do product rule once, right? I just have 2 factors, this factor and this factor, right? So you guys take a second and find me the second derivative now. All right, so if we're using product rule, the derivative of the first, e to the x, times the second, so that would be times x squared plus 2x, plus the first, which is e to the x, times the derivative of the second, so that would be 2x plus 2. Now, again, I can factor an e to the x out of both of these terms and clean this up a little bit. So e to the x times, and I'll just be adding these 2 pieces together then. So I'll have x squared plus 2x plus 2x, which would be plus 4x, and then plus 2. So if I want to figure out where this graph changes concavity, I want to set my second derivative equal to 0. Now again, if this is a calculator question, I can just plug this whole thing into the calculator and find where it equals 0, where it crosses the x-axis. Or I could think about this in terms of each of these factors. I can set each one individually equal to 0, like this, x plus 2. Now this one, if I try to solve by taking the natural log of both sides, I will get x equals the natural log of 0. Natural log of 0 is undefined, so this does not give me any answers. This one does not factor nicely, so if we're able to use a calculator, we can just graph this and find where it crosses the x-axis. Right? So let's do that. X squared plus 4x plus 2. Clear these out. So x squared plus 4x plus 2. Let's go back to zoom 6. So it crosses right there and right there. The easiest way to find those values is to go second calc, okay, this button right here on the calculator, and then we want to use the 0 feature. So it asks me a couple of questions. It asks me for a point to the left, so it doesn't matter where that point is as long as it's to the left of the point. Then it asks me for a point to the right, and then guess does not matter. So my first answer is negative 3.414. So x equals negative 3.414. And then my second answer, let's do second calc 0 again. And again, it asks me for a point to the left, a point to the right. Guess doesn't matter. So my second answer is negative 0.586. X equals negative 0.586. All right. So these are the values at which my original graph changes concavity. Okay. Let's move on to the last page then. Okay. Now this one, we can actually use the second derivative to find extrema, meaning mins and maxes. Well, to do that, we want to first find the places where the first derivative equals 0, right? Those are our critical values. That's what we've done. So let's do that. Let's find our first derivative. So that'll be negative 15x to the 4th plus 15x squared. All right, so now we want to set that equal to 0, and I can factor out a negative 15x squared. When I do that, I'm left with x squared minus 1. So let's see, this will give me, if I set this equal to 0, I'll get x equals 0. And if I set x squared minus 1 equal to 0, this will get me positive and negative 1, right? So we've got 3 critical numbers. Now, instead of putting these values on a sign chart, like we have done to find our mins and maxes, what I can do is instead find the second derivative at each of these values, okay? So my critical points occur at x equals negative 1, x equals 0, and x equals positive 1. Now, let's find the second derivative. Okay, so my second derivative, f double prime of x, will be negative 60x cubed plus 30x. And again, it might be easier to see what happens if I factor this and make this negative 30x times 2x squared minus 1. So now, what I want to do is plug each of these values into my second derivative. Okay, that's going to tell me whether my original function is concave up, concave down, or nothing is happening. All right? So, if I plug negative 1 into my second derivative, right, I can see, actually let's start with 0. Let's do 0 first. If I plug 0 in, this will be 0, 0, minus 1. So I get 0. Oh, wait a minute. 0 is the one I didn't want to do first. I am sorry. I want to do negative 1 first. So if I plug negative 1 in, I will get 30. And then I will get 2 times negative 1 squared is positive. So 30 times 2 minus 1, 30 times 1 gets me a positive value, right? So if that's the case, if I have a critical point where the first derivative equals 0 and the second derivative is positive, if the second derivative is positive, that means that my function is concave up, right? So if my function's concave up, it looks like this. But I also know that the first derivative equals 0. So we're talking about this point right here. If that happens, I have a relative minimum value there. So our criteria there, where the first derivative equals 0 and the second derivative is positive. Okay, wherever that happens, we have a relative minimum. And that was part of the chart that we did on the other page. So let's do x equals 1 next. If I plug 1 in, I will have a negative value here, and I will have a negative, no, I'll have a positive value here, yeah. So I'll have a negative value times a positive value. That would give me a negative value. If that's the case, my second derivative is negative. That means my function is concave down, but my first derivative equals 0. That means we're talking about this specific point here. So I have a relative max at that point. Now let's do 0. So if I plug in 0, I get 0 times negative 1, which is 0. Right? So the sign of my second derivative is 0. If that's the case, if both my first and second derivative equals 0, we can't draw any conclusion. Okay? And that is what we had in the chart on the front. So we actually have two options now to find relative mins and maxes. Okay? We can find our first derivative, take our critical numbers and put those on a sign chart, or we can take our critical numbers and find the sign of f prime, the sign of f double prime, the second derivative at each of those, to determine concavity. Right? Let's take a look at our last example then from a graph. So here we are given the graph of a derivative. I want to figure out where my original function is concave up, concave down, and where it has points of inflection. So real quick, let's determine what our first derivative test would look like. So if I want to find critical values or critical numbers, that's going to be where first derivative is equal to 0, right? That's going to be there, there, and there. So this question does not ask us to do this, but I just want to do this real quick. So I don't know, that looks like negative 2.8, maybe 1.6-ish, and 4.1. So those are my critical values. Now, my first derivative is positive here, my first derivative is negative on this interval, then positive on this interval, and then negative on this interval. So what that tells me about my original function is that it's increasing here and here, decreasing here and here, and then my original function would have a relative max here, a relative min here, and a relative max here. Now we want to do something similar for the second derivative. Okay? I want to find places where the second derivative equals 0. Well, the second derivative is the slope of the first derivative, right? So what I want to find is where the slope of the first derivative equals 0. Well, that occurs right here and right here. Right? That looks like that occurs at negative 1 and at 3. Okay, so this is all based on the idea that the second derivative is the slope of the first derivative. So if I look at the slope of this function, okay, the slope is negative all the way until I get to negative 1. The slope then is positive in between negative 1 and 3, and then the slope is negative from 3 on. Right? So now what this tells me about my original function is that my original function is concave down. So we can say f is concave down on the interval -infinity to -1 and from 3 to infinity. And we can say it is concave up on the interval -1 to 3. And then we have points of inflection at x equals -1 and x equals 3 because my function does change concavity there. All right. So tomorrow we will do some more practice with this.